All right, welcome to this invited session in the probability statistics section. Our first speaker, first of all, I should actually make an announcement. Many of you probably already figured this out. The third talk is canceled since Martin Hare, one that feels valid, already spoke earlier in the section, earlier in the comments. All right, so our first talk for the afternoon, though, is Russ Lyons from University of Indiana. He got his PhD in 1983 from University of Michigan in harmonic analysis. And then he drifted into probability, and we're happy to say he stayed now, it seems, at least mainly. He was a Sloan Fellow, won a Sloan Award. He was a Miller visiting professor at University of California. He won the Indiana University Trustees Teaching Award. He is a fellow of the Institute of Mathematical Statistics and was a medallion speaker, a fellow of the AMS, and now he is an invited speaker at the ICM. I think many people here know his work on trees and Markov processes, but you should also check out his paper on the spread of evidence-poor medicine, which is another thing that's interesting. So without further ado, I give you Russ Lyons.
Thanks very much, Jonathan. It's nice to be here. Can everyone hear me pretty well? Okay. I hope you've had a chance to look at this slide while I was being introduced. And I hope can you all read the captions at the bottom? You may need to stand up to see them. And during my talk, you may also need to stand up sometimes to see the very bottom line. I apologize for that. So I'm going to talk about determinantal probability, or more precisely, determinantal probability measures and determinantal point processes. And there's a lot one could say, and I say a lot more in my ICM paper, but I'm going to focus on one particular aspect here. And before I get to that, let me mention and illustrate with these two pictures that it's a topic that has arisen in areas of mathematics. Thank you. Although, then the top is going to be cut off.
We can get to the cycle more easily.
Yeah, we'll have equations. It'll be a bad idea. Sorry, Russ.
Well, so it turns out that determinantal probability has become of interest recently in machine learning. So it's one of these things that, very surprisingly, some topic in pure mathematics suddenly becomes of real, genuine applied interest. And I'm going to talk about that just a little bit here. So here you see two photos, or rather samples of two photos. There are 225 points and little discs around them on the left and on the right, same number of points. But you can see, I hope, that the one on the left, you can see a lot more of the picture. The points, they're both at random, are spread out a lot better. The one on the right, the caption there says uniform sample gates. So there's some gates, I'll show you the whole picture in a moment. And those are just 225 uniformly distributed independently points on that rectangle, okay? And on the right, instead, they're distributed by a determinantal point process with a Dirichlet kernel. So I call it the Dirichlet sample gates. They have the property, and this is why it's of interest in machine learning, that they naturally spread out better. And this is also going to be, in an intuitive way, what's behind theorems I'm going to tell you. I'm not going to say too much more about that in terms of machine learning, but there are various diverse uses of it now. So this is the picture that you're getting samples of. These are actually called the sample gates at Indiana University. It's the main entrance at Indiana University. And they're named after the samples. In fact, people, when they visit and I tell them that, they don't usually believe me. They think I'm making a joke until I show them the plaque that's posted on the gates that gives you the names of the samples after which they're named. In fact, one of the samples still works at Indiana University. Not one of these. Anyway, so I'm going to tell you about one theorem and some corollaries it has, and I'm going to start by giving you some sample corollaries of that theorem to give you an idea of its diverse applications in nature. And then I'll tell you what's behind it. Also, I'm going to start by not defining all the terms, so just you can see them all at once. And then I'll go over them slowly and define the terms. So here's the first corollary. for each subset A of the unit interval with the Lebesgue measure absolute value A. There's a set of integers of Bernoulli-Maillevin density absolute value of A, measure of A, such that the set of corresponding complex exponentials is complete for L2 of A. Okay, I'll define all these terms in a moment. But that's corollary 1 of this mystery theorem. Okay? Here's corollary 2. Given any infinite locally finite graph G, almost surely, simple random walk on each tree in the wide uniform spanning forest of G is recurrent. Again, I'll define all terms later. Doesn't look at all like corollary 1, right? And I'll tell you the history of these when I detail them. Corollary 3 is unfortunately just a conjecture because the theorem has a conjectured extension, and then this would be a corollary. So corollary 3 says, let Z be the set of zeros of a random complex Gaussian power series in the unit disk. Then almost surely, the only function in the Bergman space that vanishes everywhere on Z is the zero function. Okay? So those are the 3 corollaries I'm going to talk to you about and what is behind them. So now let me give you the definition of the terms in corollary 1. It's about integers. So we're going to use the Fourier isomorphism between little L2 of Z and big L2 with respect to the Lebesgue measure of the unit interval. That, given by this map, the standard orthogonal basis of L2 of Z, 1 at n and 0 elsewhere, is mapped to the function E sub n, and E sub n is the function whose value at t is equal to 2 pi I nt. Right? That is the standard complex exponential corresponding to the integer n. So that's a theorem. It's not hard to prove. Fourier's theorem, more or less. That's an isometric isomorphism. So in particular, since we started with an orthonormal basis, we get an orthonormal basis, En. Okay? Now, I'm going to focus only on part of being a basis, the fact that it's complete. In other words, if I take the linear span of En and take the closure, I get everything. Oh, so it's redundant. The closure is everything, or if I don't take the closure, it's dense. Okay? Equivalently, if I have a function f in L2, which is orthogonal to all the ENs, then it's 0. Okay? So those are just 2 ways of talking about completeness. Now, let's look at some other examples. Suppose we consider just functions on the interval 0 to a third. Then, clearly, E sub n for n being a multiple of 3 would be a complete set. In fact, it would be an orthonormal basis, but a complete set for that, right? And that's very natural. You cut down space by a third, you increase frequencies by 3. You're taking only a third, in an obvious, intuitive sense, of the basis vectors you started with, or the complete set you started with, and you get a basis for the complete set for the smaller space, right? That's very nice, but things aren't always so nice, in fact. So Kouzes proved that there exists a set of positive integers of density 0, so that those complex exponentials are complete in L2 of 0a for every a strictly less than 1. So the ordinary density is not at all capturing what you might need in order to be a complete set. In fact, this question has a long history going back to the 30s, and it was the research culminated in a theorem of Bernoulli-Maillevin, which I want to tell you. Now, the details here are not going to be important. There's not going to be a quiz later. But just to give you some sense of what is involved, they determined the correct notion of density, not the ordinary notion. And so it involves something called aspect of an interval, just the maximum and absolute value of the endpoints over the minimum. That tells you something about its shape versus how far it is away from the origin. And for a discrete set of reals, the Bernoulli-Maillevin density of S is the supremum of D such that I'll just describe this in words. There is a relatively fat set of intervals that captures at least D, a density D of your set S. So relatively fat is given by this condition, that the aspect doesn't tend to 1 too quickly. Anyway, the details are not important. The important thing is there's some somewhat sophisticated notion of density, and it's the right net notion. So this is their theorem, that A be an interval. Okay, I was talking before about any set. Here's an interval in the real line. If En is complete for L2 of A, then the Bernoulli-Maillet density is at least the measure of A. And if the Bernoulli-Maillet density is strictly greater than the measure of A, then the En is complete. They do not talk about the critical case. The critical case cannot be decided by density alone, right? You could remove one point from the standard orthogonal basis and it's no longer complete. Removing just a single point. Density is not enough for the critical case, okay? But this does determine the critical density. So, now I've defined the terms. I can restate corollary 1. It's a corollary of a theorem in my paper in 2003. It says, given any measurable set A, there exists a set of Bernoulli-Maillet density equal to that measure, for which the corresponding complex exponentials is complete. Okay? Now, unlike for intervals, this is not sharp in general. Okay, so that's corollary 1. Any questions? Okay, corollary 2 is about trees. So here's a finite graph, all the edges, red and black. The edges in red form a spanning tree of that graph. So this graph is connected, and this is a maximal set of edges without cycles. Or another way of saying it is, it's a set of edges such that you can get from any vertex to any other vertex by traveling along the tree in exactly one way. Now, I'm interested in the analog for infinite graphs. For finite graphs, we could take one of these uniformly random. It turns out to be very interesting, and it's clear what that means. But for infinite graphs, it's not quite as clear what it means. And there turns out to be two natural ways of defining it, on the left and on the right. The one on the right is going to be more important, but the one on the left is the one that's easier to describe. Let me start with that. So I have an infinite graph, goes on forever, and I consider finite graphs. So consider all the purple vertices, and that induces some subgraph here, all the edges in green and blue. I take a uniformly chosen spanning tree from there, and that's what I've shown in the blue. Okay? Then I take a larger subset of vertices and take a uniform spanning tree and so forth. So I get a sequence of measures on subsets of the edges, each supported by a spanning tree on just a part of the graph. And I want to look at a limit. So there's a weak limit. What that means is if I focus just on a finite set of vertices here and look at which edges happen to be chosen in my spanning tree as I take larger and larger sets, then that sequence of distributions has a limit. And that's true for every finite set, and so therefore it's consistent, and Kolmogorov theorem says there will be a limit. Okay, well you have to prove some of those things, and P-Man will show that in 91. The same is true over on the right. What's happening on the right? Well, before I take this spanning tree, I have this set of vertices, and then I have all the vertices outside, which are this dark pink color, which are adjacent. Identify that outside boundary to a single vertex. And so that's why these edges here got dashed, because they're really not there anymore. It's just a single vertex. That's called wiring the boundary. So I take that finite subgraph, I wire the boundary, then I take a uniform spanning tree. So that's what you see in blue. So it doesn't look connected. That's because I'm not drawing it with the identified vertex as a single vertex, okay? But it is. But again, you take a window and you look at the edges you get, and again the limit exists. Always. Okay, and so on the left it's called the free uniform spanning force, and on the right it's called the wired uniform spanning force. Sometimes they're the same, and sometimes they're different. It's known. basically when that happens. Let me just mention one example. If we had a regular tree of degree 3, the free spanning force is trivial. You just always have all the edges because every finite graph is a tree, and that's the only spanning tree it has. Whereas in the right, when you identify the boundary is actually pretty big, and you might expect it would have an effect even in a limit, and it does. So I'm going to be looking at the wired spanning force. Okay, that was one of the terms in the corollary 2. But first I want to tell you a theorem. With a Hegstrom, if the underlying graph G is a tree, doesn't have to be regular, then when is the wired spanning force everything? Well, it turns out that happens with almost surely or positive probability at the same time. It's if and only if simple random walk on T is recurrent. So that just means from every point, you take a uniformly chosen random neighbor, walk there, and then independently choose a uniformly random neighbor, and so forth. That's simple random walk. And recurrent means you come back to where you start, infinitely often the probability 1. So, corollary 2 was the theorem of Morse, which confirmed a conjecture in a paper with Benjamini, Paris, and Schramm that says, for every G, almost surely, every tree in the wired spanning force on G is recurrent for simple random walk. Now, we made that conjecture because there's a lot more one can say about the connection between random walk and these random spanning trees. And it turns out, if you go into that, you see that the trees in the wired spanning force are somehow critical. And it's natural to conjecture this. And we verified some special cases. Anyway, using Hegstrom's theorem over here, criterion, we can reformulate Morse's theorem in the following way. For every G, almost surely, if we take the wired spanning force on G and do the wired spanning force on every tree that we get, it doesn't change. Okay? Corollary 2. Any questions? All right. Conjecture corollary 3 on 0 sets. So D is a unit disk. Gn is going to be a random power series. The coefficients are independent, standard, complex Gaussian random variables. So real and imaginary parts are independent, normalized so that the complex variance is 1. Well, that doesn't matter. And Z is the 0 set. So that's a random point set because G is random. Now what's the Bergman space? So we're talking about, notice I should have said, the ANs are nice, and Z in the unit disk, so this decays exponentially fast. This converges almost surely, not a problem. The Bergman space consists of the analytic functions in the unit disk that are square integrable with respect to the big measure. And for any such power series, if you compute the square integral, it has that form. So absolute AN squared over n plus 1. So in our case, the ANs being complex Gaussian, it just barely fails to converge, right? So these functions we're looking at, the random functions, are not in the Bergman space. So here's our corollary 3 restated. The Z be a set of zeros of this random complex Gaussian power series. Then almost surely the only function in the Bergman space that vanishes on C is a 0 function. So there's some, you can see here, there's some sort of almost critical nature. The theorem, the corollary 1 about the Bernoulli-Mallet density was pretty explicit about criticality, and I didn't have time to tell you about why corollary 2 also had a critical nature. But this is also critical. Okay, questions on corollary 3? Okay, so now you know what they mean, but you probably still don't see how they're related to each other. And in fact, the first one didn't even look like probability. Right? I just said some set exists. Well, there is probability behind it. It's proved by the probabilistic method. This set S is chosen at random. So there's some probability measure, P superscript A, on subsets of Z. And almost surely, it picks a set with the properties we want. Okay, so now these are some probability. Now, this measure, it turns out, is a determinantal measure. So is the wide spanning force measure from corollary 2, and the random zero set from corollary 3. Okay, now at least you see that there's a relationship, but they still probably don't look so similar to each other. But I need to tell you what determinantal probability measures are. So the E, well, I should say the third one is in the continuous context. So first I'm doing the discrete, corollary 1 and 2. So let E be an enumerable set and H be a closed subspace of L2 of E. We can have the orthogonal projection onto H, piece of H, and put square brackets around it for the matrix in the standard orthonormal basis. So for every element of E, you have the vector which is 1 at E and 0 elsewhere. So it turns out that there is a unique probability measure, P superscript H, on subsets of E defined by that equation in red. For any finite set D, the chance that my random set B contains D is a determinant of a finite matrix. I just take the matrix PH and I look at the rows and columns indexed by D. So it's a D by D matrix, and I take this determinant. This has some history, but in this general context, it's more general than this actually. It was introduced by Maki in '75, who's a physicist. So let me do an example. Suppose I have two distinct elements, E and E prime. What's the chance that I include E and E prime? So here is the column, here's the row, so here's the column indexed by E, here's the column indexed by E prime, the row indexed by E, and the row indexed by E prime. And so I look at where those intersect. And I take a determinant. What do I get? Well, the product of the diagonal elements. Now those are both 1 by 1 determinants, so they have an interpretation as single marginal probabilities. I multiply those. And these two are complex conjugates of each other. So I'm subtracting something non-negative. So this is very important. And this is behind those pictures at the beginning. This says that E and E prime are unlikely to be both chosen if the two vectors PH1E and PH1E prime are close to each other. There's a negative correlation here. Okay? There are more general properties that we'll need, but I can't prove or state. Now, I hope you can all see that. It's a trivial fact at the bottom here. Suppose H, I didn't give any examples except this calculation, this general calculation. Suppose H is everything. Then the matrix is the identity, and all these determinants are 1. So I just pick everything with probably 1. It's a deterministic measure, okay? I'll need that trivial fact. Now, I don't have time to explain everything in this picture, but let me give you a more general example. Suppose it happens that H has dimension R, dimension is finite, which I'll call R. In this case, in the picture, it's 2-dimensional, and E has size 3, because that's 3-dimensional space we live in. And the 3 unit vectors are projected here onto H. Hope you can see that back there. Now, what's the chance that my random set is equal to these points, to a given R set, E1, 3R? Well, the determinantal definition said the chance that I contain R points. But if I had more than R points, and I project those onto H, they're linearly dependent, the matrix will be singular, the determinant will be 0. So there's no chance of having more than R points. So containing R points or equal to R points is the same. And the definition had only one pH, but pH is idempotent and self-adjoint, so I can put another one over there. So that's a Gram matrix. It's a square volume of a parallelepiped, and I didn't tell you why there's such a probability measure, but at least in this case, you may have once learned that certain squared areas volumes add up to 1, but anyway, we don't really need that. It's just why this is a probability measure. The important thing to note here is that this determinant is non-zero if and only if these projected vectors form a basis for H. Right? I have R of them, and they're linearly independent. So the theorem that's behind those two corollaries, and an extension that would give the third, is that a similar thing holds when H is infinite dimensional. I take this subspace H, I take my random set B, I project the unit vectors onto H. I'm not saying anything about a basis, that's somewhat problematic in infinite dimensions, but it's almost surely complete. Or another way of saying that is, if I have any vector V in H, and it's orthogonal to all the unit vectors that correspond to points I pick, then it's 0. Any questions on what the theorem says? So this is saying something about how those points can be picked, okay? So it's restated, now corollary 1. So let me prove corollary 1 from the theorem. E, the ground set is going to be the integers. What is H? Well, I was given a set A in the interval, and I was interested in L2 of A. So there was this Fourier isomorphism. A is a subset of 0, 1. I can think of L2 of A as a functions in L2 of 0, 1 that vanish outside A. So I take the Fourier transform of all those functions. That gives me a subspace H in L2 of Z. All right? I want to pick an S, a set S of integers. So, this probability measure picks a random set of integers. Use this space H, called B. And I'm going to show that if I take S to be B, then that will work almost surely. Okay? So I need to verify the conditions of the corollary. So I'm going to show this is complete. So let F be in here, and suppose it's orthogonal to all those. I'm going to show it 0. Well, F is in here, so by definition of H, F hat is an H. And it's orthogonal to the E ends, that means F hat is orthogonal to the 1 ends, to all N and S. Now, what does the theorem say? Well, that looks very much like the theorem, right? I have something in my subspace, it's orthogonal to all these points I pick, so it's 0. So F hat is 0. So that means F is 0. Okay? So I've shown it's complete. Now, what about the Bernoulli-Maillet density? I don't have time to give a complete proof. I didn't even let you study what it means. But what is, let's think about the ordinary density first. What is the chance that I pick a given integer, n? Well, that's this 1 by 1 determinant. Okay, this. Now, what is this? Well, use the Fourier isomorphism to put this back where it came from. H becomes L to A. Once of n becomes En. It's this inner product. What is that inner product? Projection on L2 of A is just killing everything that's off of A, multiplying by the integrator of A. So I just take the multiply by 1 sub A, take the complex conjugate 1 sub of E sub n, integrate, I get integral 1 sub A, that's the measure of A. So the chance that any integer belongs to my random set is just the measure of A, by definition. In fact, it turns out that P sub H is a stationary ergodic process on Z. So the ergodic theorem tells us that the ordinary density of this random set is equal to this chance of picking 1 point, measure of A almost surely. That's the ordinary density. We wanted to do something better, right? Something that was in the nature of criticality. Well, it turns out it's quite easy to show that ordinary density is a lower bound for the Bernoulli-Maillet density. And negative association, which is a property that's stronger than negative correlation, holds for determinantal measures. And it makes this random set quite regular. And for example, it gives a Gaussian upper bound on the difference between the number of points of this random set in an interval and the expected number of points. And then you can show the upper bound, matching upper bound pretty easily. Sat does it. Okay? So that's corollary 1. Now what about corollary 2 on trees? Well, it turns out I actually need to use a dual form. This is quite elementary, but I don't have time to do it for you. It's quite elementary to express this dual form. And this says, I'm going to project the other way. I'm going to look at L2 of B and project everything in H onto L2 of B. This is coordinate projection, right? So given any vector H, I just set all the coordinates off of B to be 0. Trivial type of projection. And I'm only going to need this one form of it. Then if I take everything in H, project on L2 of B, that's dense in L2 of B. Almost sure. Okay? So here's corollary 2 of Morris restated. And this is the trivial fact that I'm going to use. If I do a determinantal measure that corresponds to a subspace which is everything, then I just choose everything with probability 1. So G is a graph, got vertex at V, edge set E. This ground set E of the theorem is just the edge set of the graph. So I'm going to think of a spanning tree as a set of edges because I include all vertices and only some edges. Now I need to orient each edge, it doesn't matter how. Given a vertex, the star at that vertex U is defined to be a vector in L to V, given by the sum of plus or minus 1s of 1 to B. So if here's U, here's some of the graph, here are the edges incident to U, and I don't know how they're oriented, but I put plus or minus 1s on them so that taking into account orientation, they would all point out, say. Okay? That's the star U. And it's relative to the graph G. Take the closed linear span of all the stars, and we'll call that big star of G. So it's a remarkable fact that this wide spanning force, I told you it was determinantal. Well, this is how it's determinantal. It's a determinantal measure corresponding to orthogonal projection on the star space. This actually has a long history. Remember, that's a bunch of determinantal equations. The 1-by-1 case is due to Kirchhoff in 1847. 2-by-2 is due to Brooks, Smithstone, and Tutt. The general case, Burton and Pimentel, and the finite graph case in the general case in that paper. So it's not obvious, but actually it's not hard to prove. There's a short proof of that in my ICM paper. Related to Kirchhoff's, related to the matrix tree theorem, often attributed to Kirchhoff. Okay, so now here's a fact. What do I want to do? I want to project things on L2 of B. B was some subset of E. So it turns out this is very simple here. Here's my star again. And I have some subset of edges. So say I take away the ones that are dashed there. B is the edges that are left. What's this star corresponding to those vertices in the edges that are left? Well, it's just the projection of the original star, right? Because I just set to 0 the other coefficients. So I take a star in the whole graph. I'm looking at a subgraph. I just get the star of the vertex by this orthogonal projection. So stars go to stars. So if I project everything in the star space, I get something which is dense in the star space for the subgraph. Just by definition. Okay? What does the theorem tell us? It says for almost every B, when I do this, I get something which is dense in L2 of B. So, can you see the yellow? No, you can't really see yellow. Yellow here and yellow here. You can't see that very well, can you? Sorry about that. It was supposed to make it easier. To follow the logic. These two things are very closely related and tell us that these two spaces have to be the same. Almost surely. They're not always the same, but according to the theorem, the B's that I pick, I almost surely get the same thing, right? What does that mean? The determinantal measure corresponding to this space is everything. So it's trivially concentrated on all of B. That means I take the wide spanning force and do it again, nothing changes. That's the corollary. That's just there. Okay? All right. Now, how are these related to conjectured corollary 3, and why is that only conjectured? So those were discrete, and corollary 3 is continuous. So something else has to be done. But most of the theory of determinantal measures carries over. But I had to use this dual form to get corollary 2. It turns out, in the discrete case, you can get one from the other with no problem. But it's actually proved using the dual form. And that duality doesn't exist in the continuous setting. There's a duality, where you pick a subset. In the discrete case, you could take the complement. If you have a point process, you do not want to take the complement. So we're kind of stuck. Let me tell you about determinantal point processes. So now, this is really just an extension of the denumerable case. Let E be a locally compact polar space with a Radon measure. For example, the big measure on Euclidean space, or some part of Euclidean space. The case we were doing before was counting measure on a denumerable set. So we're going to talk about simple point processes. In other words, counting measures on discrete subsets. So a point process is determinantal if there exists this magic function k of two variables, such that for every little k, the k-point intensity function is a determinant. Now what is a k-point intensity function? Intuitively, it's the probability density of finding points at those locations. There may be points elsewhere, but you include at least those points. And that should be the determinant where you take k at those points, this kernel with all pairs at those points. And in this case, we'll write p superscript k for the law. Now, there is a formal density of k-point intensity function here, but if you haven't seen it before, I don't recommend studying it too much because it's not very intuitive. Now for us, k will be locally square integrable. So by the way, there are a lot more technicalities in the continuous case. Hermitian, and define an orthogonal projection on the sum closed subspace H as an integral operator. So given some function f in L2, it's mapped to some other function via this integral. And k is the kernel of the integral. Okay? Now, this is actually quite similar to what we were doing before. If mu is counting measure, kxy is just the xy entry of the matrix. And this is just summation. Now, we need a little formula here. Projections are idempotent. So if you write out what that means, you get this equation almost everywhere. And you could redefine k so that it holds them everywhere, which we'll do. Now, let's write k sub z of x to be k of xz. Then what did we do? This is what we're getting on the left-hand side. And we're getting it by integrating the kernel against some function. So we must get something in the space H. So kz is an H. Okay? Now actually this is familiar also. In counting measure, this is just a column of the matrix, which is the projection of the basis vector, right? Now, using the fact that it's a projection, if we start with something in H, then we get this equation. And notice that this is, using this new notation, we can also write this as the inner product of H with k sub x. Take the interchange these and take the complex conjugate because the k is Hermitian. So this holds almost everywhere. And again, we can redefine H so that it holds everywhere. So in other words, k is a reproducing kernel for H. Okay. Now, the conjectured extension of the theorem that would give the conjectured corollary 3 is something I made with Yuval Perez a few years ago. And it says, in this general context, for almost every sample x, the set of these vectors, k sub x, is complete in H. In other words, if little h in the subspace satisfies h of x equals 0, same thing as the inner product being 0, for all x in question, then h is 0. So now I can tell you corollary 3 again and prove it modulo this conjecture. So recall what the Bergman space is. And here's the corollary 3 stated again. So here would be the proof. E is the unit disk, and mu is the unit of the big measure on D, and K is that kernel, called the Bergman kernel. Turns out that it gives an orthogonal projection onto the Bergman space. Now, there's a much deeper theorem that says that what you get is this random zero set Z. That's a theorem of Paris-Viereck from 2005. Much of determinantal probability has to do with showing that specific examples are determinantal, and that's often quite an achievement. And then you get all such information, calculations you can do. This being an example. So Z, I told you, was determinantal. Now I said why, or how. So now you can apply the conjecture. Z is X, and if I have something in the Bergman space and it vanishes at Z, then it's 0. And that's what the corollary says. So in the remaining time, I can tell you a couple of other corollaries that would follow from this conjecture that we did conjecture. We conjectured several specific examples, which is why we, and we had reason to believe them, so why we believe the general conjecture as well. So here's one. Mu is the big measure on the real line, and k of xy is this function, sine of pi xy over pi of x minus y over pi of x minus y, pi times x minus y. That turns out to project onto what's called a Paley-Wiener space. It's occurred in an earlier theorem without the name, and defines what's called the sine kernel process, which is scaling limits of eigenvalues of random matrices, for example. Then it would follow from this theorem that almost surely, for almost every x, the only h in L201 such that h hat, the Fourier transform, vanishes on x is 0. Now, since we're talking about this nice classical situation, you can apply the Bernoulli-Maillard theorem. But similar to what I showed you before, this set X does have Bernoulli-Maillard density 1, almost surely. That's the critical density. Bernoulli-Maillard doesn't tell you anything about what happens at criticality. So you can't learn anything, but it tells you you're in the right ballpark. But Shubro-Ghosh did prove this case. Here's another one we conjectured. So that's not a theorem. Let mu be standard Gaussian measure on the complex plane, and k be this kernel, e to the zw bar. This gives an orthogonal projection onto what's called the Bergman-Fock space, which consists of the entire functions that are square integrable with respect to Gaussian measure. And the determinantal process it defines is called the Genebra process. It's also a scaling limit of eigenvalues for random matrices and other things. And so the conjecture would say that almost surely, for any sample, the only h in the Bergman-Fock space that vanishes at all those points is the 0 function. Now, the Genebra process has density 1 almost surely, on the one hand. And on the other hand, the critical density for zeros of the Bergman-Fock space is 1 in various senses. This is known going back to von Neumann. This case has also been proved by Shubro-Ghosh. So the two instances that were proved, he proved a more general result that our conjecture holds whenever this determinantal process is rigid, which means that the number of points in a ball is measurable with respect to the outside of the ball. The points, locations of the points outside of the ball. So that's the end of my story. You can read more details and other things about determinantal measures and some other references to other surveys from my ICM paper. My paper is sort of a survey of theoretical aspects and these conjectures and some other things, but there's other surveys with all sorts of examples that other people have written. So thank you for your attention.
there any questions?
When you prove that the this sequence of restricted cosine functions or whatever is dense in L2, do you have presumably a lot of quantitative information about how well a finite collection of them do? Is it because you get this very 0-1 thing, but I mean it's not orthogonal, obviously. Is there quantitative information about how well you can do with finitely many of them?
So that's a good question. And making quantitative my theorem more generally would be interesting. So first of all, the method of proof doesn't give any at all. Second, you can't expect too much because of the natural randomness. With some probability, you could get sort of any points somewhere. However, and so there also, you don't have things like a respaces or frames or anything like that. So I'm not sure what one might look for. There is an old theorem of Bergman and Sofiri, which is similar to what I stated. It's reviewed in my ICM paper. That gives you a factor of 2 to the 8 worse getting your set, but it gives you some quantitative things, which has been extended by others and is related to Caddis and Singer, so I think there's a pretty sharp thing now. But it doesn't give the critical case. So I think it would be interesting to, if there were some way to incorporate both in one theorem. But I don't really know how to formulate what that would be.
What if you tried to constrain the L1 with the coefficients, like in Lasso? So you did the best L2 approximation with opposed to constraint, an L1 normal constraint, which would then force you to have only a few non-zero coefficients. Just thinking.
Any other questions? Any other questions? All right, well then, let's thank Russ again, and let me give him this present from the organizers. All right, we'll reconvene at 5 after the hour for the next talk.